We're going to talk about A to D converters in this video. And there are three kinds of, or general kinds of A to D converters that you ought to know about. One of which is the parallel conversion A to Ds. And falling under this is one thing that we call a flash ADC, which I'll talk about more in just a second. Another type is the feedback A to Ds, which includes the type that you're going to build in the lab. This is a successive approximation register, and also tracking A to Ds and things like that, which you won't be building, but this is the one that you will be building in the lab. And then there's integrating A to Ds. And one kind that we'll actually talk about is the dual slope A to D, which you could build, but you won't be doing that. So these ones, the parallel ones, the flash ones, are fast, okay? But it's hard to build them with lots and lots of bits. These integrating A to Ds, including dual slope and delta sigmas and things like that, are slowish, but they have the best resolution. Oops, I can't spell best resolution. And instruments like your voltmeter in the lab use these because they reject interference that's synchronous with the clock or the line that they're using to do their thing, which we'll talk about more in a second. This is the one right here. This SAR is fairly inexpensive, but can be good, and you're going to build this one. Okay. All right. So let's actually talk about the flash ADCs first. Okay. The idea there is that you have a voltage coming in that you want to measure, and then you have a resistor ladder with some resistors that are going to divide that voltage up into a bunch of different points. Okay. And we'll just talk about it as though we're going to have a 2-bit A to D. So you have 4 voltage possibilities. And then we're going to pull off each of these spots right here and run them into a comparator. Oops, I actually blew this. I wrote this down wrong. This is not V in. This is a V reference. Okay. Reference. And then V in is actually going to come in over here. Okay. And we're going to use that V in into a comparator. And this will tell me whether V in is above or below, this particular voltage right here. It tells me that. Now, of course, I'm going to jump over here and go down and do this again with another comparator. Okay. And then we're going to do it again finally over here. One more time. Oops, I'm not drawing very well today. There we go. Going to run that into that bit of the comparator. And then what this is telling me is that I'm comparing V in with all these reference points. And all I have to do is, if we want to set up our bits like we talked about the other day, then you make these resistors these values right here, and you sort of have these half-width bins at the top and bottom for the R/2, and you have the R's in there to drop down the same voltage. And I'm going to be able to tell where the input voltage is by the outputs of all of these comparators. So from this, I'm just going to run this into some logic, which is going to look at all those inputs, and then that's going to tell me these 2 output bits, Q1 and Q2. Whoops, again, I can't write today. Q1 and Q2, okay? So this is super fast because I have my voltage right here, and it's kind of instantaneous. I've got these all set up already. These inputs are steady. They're always the same. They never change, and those are the inputs to this comparator. And basically, as fast as I can do this comparison and the logic can process, which, as you know, can be super fast, I can get output bits. Okay. So if I want to have more bits, of course, then I need to have more comparators here and more resistors. So I need 2 to the n resistors, and I need 2 to the n minus 1, minus 1 comparators. So if I want a 16-bit encoder, suddenly this gets hard because I have to have all these resistors matched and everything. So it's hard to do for lots of bits, but it's super fast, and that's why something like your scope, which is an 8-bit digitizer, is uses something like this. Okay, so we're gonna leave it alone now. That's called a flash ADC, and we're going to talk about another kind, the other kind that you're not going to build. We'll talk about the SAR last. So now we're going to talk about integrating A2Ds. Okay. So the particular kind that we're going to talk about is called a dual slope A2D, and you'll see why it's called that in a second. What you do is you take your input voltage and you run it through something that converts that voltage to current. So I'm just going to call that a V to I. Okay? We actually made a current source out of a voltage before using an op amp, right? So we don't have to go into the details of that. And then what you do is you take that current that comes out of here, proportional to your input voltage, right? And you have a switch. And that switch goes over here and charges a capacitor, which is grounded on the other side. So what you do is you charge up that capacitor for a little while, and so let's draw that. Okay. And I'm going to arbitrarily here say that I'm going to start charging at this time, and I'm going to charge up the capacitor for a fixed amount of time, this fixed number of clock cycles, say. Right? And what that means is that I have a certain time that the charging happens, which is fixed. Okay? And if I have a low voltage, perhaps, so a small amount of current coming in, then it would follow the black curve. If I have a larger voltage coming in, so therefore a larger amount of current, it would follow the blue curve. Okay? So this is, this is big V in, and the black one is small V in, which means small current to the capacitor, right? And then what I'm going to do is I'm going to throw the switch over to the other side and build some stuff over here that's going to discharge the capacitor. So in particular, I'm going to have a current source with a fixed current to ground. Okay, so this is I. And what I'm doing here is when I throw the switch over to this position over here, that means it's discharging via this current source, and it's going to discharge at a constant rate. Okay, just like we charged at a constant rate, this time I'm going to discharge it at a constant rate, but I'm going to discharge it at a known constant rate. Okay, no matter what V in was, this V out, this discharge now only depends on this current source that I built into the circuit, right? That didn't know anything about V in, right? And what I'm going to do is I'm going to watch this capacitor discharge. Okay, and so, for example, let's say that it discharges at some other rate. Okay, so I'm gonna choose a slope like this. Okay, and if I had the blue one, it would discharge at the same slope now. So these two here, these two slopes, the blue one and the black one on the right-hand side here, are the same slope because it's the same current source, no matter how much this capacitor got charged up. Well, as those discharge now, what I'm going to do is I'm going to watch this voltage right here. I'm going to watch the voltage at the top of the capacitor, and I'm going to feed it into a comparator, okay? And say I put the plus here and the minus here, and I put that at ground, so I'm going to compare it to ground. So I'm going to watch and see when that voltage crosses through ground. And when it does, the output of the comparator will flip, right? And what I'm going to do is I'm going to run this into a counter, okay? This is a counter. And I'm going to have a clock going into that counter, okay? That little thing just means edge triggered. There's a clock, and I could do this at a megahertz or whatever it is I want, okay? So this can be a fast clock if you want, okay? And then all the outputs of the clock are going out on this side. output bits, right? So I start out the whole process with the output bit set to 0. I've cleared it before doing any of this. As it's discharging, that counter is counting up. All these bits are counting up, right? And then I arrange it so that it stops counting when this comparator flips. Okay, so I'm going to call that C in or count or something. It's a logic thing that just says count. Count when that is one direction, and then don't count when it's the other direction. Okay. All right. So the point is that these output bits are timing how long it takes the voltage to get to 0 volts, which for this one will be way out here, and for the black one will be a shorter time. Right. So those are the same slope, and when those cross, okay, so this time right here, that time, is the out time or something like that, tells me how many bits I will have counted up to. And you can see that it's a bigger number of bits than this right here. And what's particularly cool about this is that if you have a clock that's actually synchronous with the 60 hertz line or something like this, this kind of scheme here, you can convince yourself, actually is immune to 60 hertz variations and things like that. It doesn't pick them up. So that's why your DVM uses a technique like this. So that's the integrating A to D. You're integrating current onto a capacitor, then you're discharging it at a constant rate, watching it, and counting as you do so, and you just figure out how much time it took. You can see that that's going to be kind of slow, right? It's not happening instantly. You have to charge up the capacitor and then discharge it. So that's why things like your multimeter are not really good at looking at super fast waves. Okay. The digital estimate, the slow version here, the integrating one, you ask yourself, how many clock cycles is that going to take? And you can tell that it's going to, it can take, depending on how big the voltage is, it could take a ton of time because you're walking it down slowly, the whole thing, right? You're walking that, you're waiting for this thing to integrate it down. So the number of clock cycles is basically your precision. So the maximum voltage, well, you have a thing that's going to count. And so if you have, basically it's 2 to the 16 is the number of clock cycles that you might have to wait for something to happen if you had a 16 bits, right? The maximum voltage would take 2 to the 16 clock cycles or so to cross 0. So that's why this is really slow. I mean, 2 to the 16 is a way better. So now finally, let's get on to the kind of A to D converter that you're actually going to build, which is called a successive approximation register. So let's write that down. I may end up spelling something around here, but successive approximation register, or SAR. Okay, so these are inexpensive, but they're relatively accurate, and they use feedback. Okay, so how is this going to work? What we're going to do is we're going to have our input voltage, right? You take your V in that you have, and what you're going to do first is you're going to make an estimate of it. Okay, you're going to make a digital estimate. Okay, and in particular, let's say you were going to be able to convert values between 0 volts and 10 volts or something like that, and you wanted to break these up into bits, right? Then you'd say, okay, the first thing I'm going to do is I'm going to choose halfway, and what I'm going to do is I'm going to compare. I'm going to actually take this digital estimate. I'm going to turn it into an analog, right? So digital to analog of this, right? So I need a D to A converter, right? And then I'm going to compare V in with my digital estimate, V dig, something like that, right? Which has been turned into analog, right? And the comparator is going to tell me which one of these is bigger, right? So it's going to tell me whether, for instance, if this was my digital estimate, it's going to tell me, is the input higher or lower, right? Which is it? Okay. And then what I'm going to do is I'm going to move on to the next bit of my estimate, and I'm going to re-estimate, okay, and repeat. In other words, the next one, let's say I found out that it was higher, okay? Then the next estimate is going to be somewhere in here, and I'm going to find out, is it higher or lower than that estimate, right? You can see I'm just moving in by factors of 2 closer and closer to wherever the real voltage is. So how are we actually going to do this in, it's kind of like a sorting algorithm almost. So how are we actually going to build this, okay? What we're going to do, letting me walk through this range, I'll draw it again, right? So let's say that we have a digital thing that's 7 volts or something like that. That's our input, right? And we're going from 10 volts to 0 volts, right? Then the digital estimate over here in these, lost my, figure out where this blue thing is. So the first estimate would be, 5 volts, right? And then the comparator tells me, no, you know what? 5 volts, which by the way would be 1, 0, 0, 0, say, and then at least if you were doing a 4-bit counter, right? So it flips the first bit, its most significant bit, and says, hey, go halfway, right? And it says 5 volts, roughly 5 volts, okay? And then it, and then it would say, oh, no, you know what? You need to keep going up, right? So then it would say, okay, let's go halfway here, which means that it would try 1, 1, 0, 0, right? If it had needed to go down, it would have flipped this bit and gone to its next one. Say the next one was the actual input voltage was down here. Okay, so say the input voltage was 2 volts or something like that. Then it would try 5 volts, and it would say, oh, I'm too high. So it would say, okay, now let's make our next one this one. I'm going to go halfway down here, right, 2.5 volts or something. I'm not drawing my levels very well, but you get the idea. It figures out, based on the comparator, walking its way in, eventually it's going to find just exactly where that matches, or at least where it closest matches. Okay. That's page here. In order to we're going to take our V in, which during this process needs to be steady. Okay. So this is not going to work if while we're doing our iterative estimate of the input of the voltage, trying to digitize it. Figure out what digital code corresponds to it. It's not going to work if Vn is actually changing. So you may have some circuitry out here that what we call a sample and hold. Okay, sample and hold. Okay, so you could imagine having a capacitor, that stores the voltage and an op amp following it or something like that. But the point is that we're not going to let Vn change as we're doing our stuff. Okay. And then, of course, I said there was going to be a comparator involved, right? So what we're going to do is have this comparator, and this is the thing that we're going to feed in that is based on some digital estimate, right? So, but what this output of this comparator tells us is, do I need to make my estimate higher, okay, or lower? Okay. In other words, if this is positive, in other words, if the output is positive, then Vn is smaller than my estimate. Right? I'll call this V dig, like I did in the previous thing. Okay. All right. So what this is going to do is now go to some logic, okay, all right, with a clock associated with it. Okay. And then this is going to be a whole bunch of bits right here. And sometimes when we have bits, the digital estimate coming out, sometimes what we'll do is we'll actually draw a line and we'll write 8. Say, that means there's 8 bits, right? And I run those 8 bits over here to a D to A, okay, which we've already covered. So remember, this is 8 bits. This is the input here, right? And this turns this into an analog signal, okay? So what this is going to do is say, okay, I've got my voltage, this V in, which is being held steady here, right? I've got my comparator. The comparator is telling this whether it should be, higher or lower, right? In other words, which way should it, flip the bit in this next estimate, and then I go into my DDA and turn this estimate into the this VDig and compare it again. So again, that's just kind of like the digital estimate in these bits right here, right? Walks through a set of things where it starts in the middle and then does a successively approximates, tries to figure out where to go. And then when it's done, when it's actually done all of these bits, flipping the bits 1, 2, 3, 4, all the way down and finding the right place to put all those bits, it has a output that says, hey, I'm all done, right? And at that point, you can go in and you can read these, right? And you can read them into a computer or with your LEDs like you'll be doing in the lab, and then you can choose to do the whole thing over again, right? All right, so if you look at how this is going, every clock cycle right here, every time you hit the clock, oops, I'm not sure what's happening there. Every time you hit the clock cycle right here, you can do a comparison with your next bit and figure out whether to flip it high or low. Okay, so to do a 16-bit SAR, how long does it take to actually go through all 16 bits? It takes 16 clock cycles. Okay, cycles to do this. That can be fairly fast, right? And if you look at one of our previous 16, okay, so that's why this is a fairly fast thing. It's fairly precise. It's not as hard as the flash ADC to do a fair number of bits, right? So it's kind of it's a nice compromise between the two. Okay. So those are the kinds of A2Ds that you're going to be looking at. I'll post some notes having to do with the particular chip that you're going to be using that basically takes care of all this stuff on this slide for you. Okay, and so you don't have to worry about too much. You just hook up the chip and it does its thing. Okay, but you'll have to read through the instructions for that separately. Okay, that's all.